So today's best practices webinar is going to be about Chapter 12. We're finishing up our best practices series for the Design Professionals ABU Online presentations or webinars. And this is the last chapter. And Chapter 12 is all about above-wall considerations. And that's exactly what it sounds like. It's going to be your fences above the wall. It's going to be your slopes above the wall. It's going to be your roadways above the wall. And pretty much anything above your wall that you need to take into consideration when you are designing your segmental retaining wall. Now, the main goal of today is basically all of these situations where there's fences above, there's roadways above, all of those above wall considerations, they're all very common. You see them in residential jobs, you see them in commercial jobs, and you see them in DOT work. So really in all sectors of our market, this stuff happens all the time. And what we're going to do today is talk about, one, how to spot those things and make sure that you guys are all aware of how each of them affects your wall design. And then we also want to know basically why it's important to consider these things above the wall. And then once you understand how important it is and when and how it affects it, we need to see how we can properly implement the considerations into our design and make sure that we're designing properly for these situations. And specifically in today's presentation, we're going to talk about four major things. We're going to talk about grid lengths at the top of wall. So, we'll be talking about how sometimes you need to extend the top layer of your grid. We're going to talk about why you would need to do that, when you would need to do that, and kind of how you can make sure you're doing it in the correct amount. We're going to talk about above wall structures. So that's going to be our fences, our railings, our impact barriers, our roads, sidewalks, anything like that. That'll be another section that we'll talk about. We will also talk about slopes above our wall and kind of everything to do with that. So it's going to range from hillsides above the wall and kind of what the limits are to those slopes, what we can allow above the wall, and if those slopes go outside of those limits, what can we do to design them properly for our wall. And then lastly, our last point we're going to talk about is plantings and basically sprucing up your wall after. How can you design for adding trees, shrubs, bushes, flowers, anything like that above your wall? It may not seem like much, but all of that stuff can impact your wall greatly, and if not handled properly, could lead to a wall failure, which we are trying to avoid. So really, I guess before I get into this, like I said, this is the last presentation of our best practices series. If you guys aren't aware, best practices is an initiative that, well, I guess best practices is the document that Alan Block worked with the NCMA to form regarding best practices for designing retaining walls. And it was all in an effort to hit a zero wall failures initiative that our industry is trying to reach. Oftentimes in wall design, we have such a big part in whether these walls are going to survive several years or not. If the wall is designed properly, then it's most likely going to get installed correctly as long as they're following the directions you give them. So by going through these best practice approaches, we can make sure that we're doing everything we can to make sure this wall is going to have a long lifetime and not fail, I guess, ever. And if you did miss those other presentations, just let me know by email, and I can get you a copy of the recording of it. I also want to note that this presentation is being recorded, so if you have any questions or you need to reference back on the video after the presentation, You can always, or I guess I'll send a follow-up email either later today or tomorrow with a link to this presentation. In that follow-up email, I'm also going to attach an evaluation form, and by filling out the evaluation form, you are able to receive 1 hour of continuing education, or 0.1 CEU, for today's presentation for attending, since this is an IACIT accredited presentation. Yeah, with that, let's go ahead and learn a little bit more about our above wall considerations. And right away, we're going to talk about top of wall grid length. So like I said before, in some situations, we are going to want to extend our top layer of grid. You can see in the example here, we've got a retaining wall. It's a reinforced wall, and outside of that infill zone, we've got this top layer of grid. You might be wondering, why do that, or why is that there? And so there's a few things. The first thing to know is, in what situations would you ever extend your top layer of grid? And there's a few different situations where that's applicable, or where that is in the best practices approach for designing retaining walls. The first of those situations is going to be in seismically active areas. So obviously, any seismic area is outside of the norm and really needs to be designed very carefully. There's a ton of stuff that can happen there, and anytime you're unsure of whether your earth is going to be stable in a seismic sense, that can impact your wall design greatly, as many of you guys know, especially you guys on the west coast of the U.S. or other coastal areas around the world. But really, in any of those seismically active areas, we want to extend the top layer, the top 1 or 2 layers of grid, sometimes more. The other time you'll want to extend your top layer of grid is when you have any type of loading above your wall. So anytime you've got a slope above your wall, that slope above the wall is going to count as loading, because having a slope above is adding extra soil, and that soil weight is going to add some pressure onto the wall, some horizontal pressure. Of course, surcharges are going to be a load on top of the wall. That's strictly a force. It can be caused by anything from roadways to even building foundations. Anything like that can act as a surcharge on your wall. And when we do see those above the wall, specifically when they interact with the retained zone of the wall, we want to extend that top layer of grid. You can see in the diagram on the right, that surcharge, that 250 pound per square foot live load, is affecting the retained zone of the wall, so that top layer of grid gets extended. Now, you may be asking, why do we extend that top layer of grid? Well, there's a few reasons why. One of the reasons why, though, is, as you can see here, you can see that on the back side of the retained soil, there's kind of this flat plane that comes up here. And what can happen is this whole teal section here is one big soil mass. All of these grids are keeping this soil together as one solid mass, technically, as long as it's compacted correctly. And basically what can happen is, when you have a lot of pressure buildup and you have all of this force behind the wall, sometimes that can hit this soil mass and it can build up and transfer straight up to the surface through this plane right here along the back of the infill zone, or back of the retained zone. And what can happen if you don't extend this top layer of grid is it can actually come straight to the surface, and lots of times you'll see like cracking or separating of the earth up here, because that force gets pushed straight up the back of that plane. Having grid cross that layer helps distribute that load equally through the soil above it, so that it's not all impacting this one point right here. So that's one of the reasons that we extend that top layer of grid. But now that you know when to extend that top layer of grid, it's also very important to know how much you have to extend that grid by. Obviously, the number one answer that I can give you is you should extend it as long as you need to meet your safety factors. But there are a few go-to recommendations we give, and that is to either extend by 3 feet or extend to 90% of your wall height, whichever is greater. So you can see we've got an 8.53 foot wall, and our normal grid lengths are 6 feet. So we can either take 90% of that 8.53 feet, or we can add on 3 feet to our 6 foot grids, whichever is greater. So that greater is going to be the 6 feet plus our 3, and that gives us 9 feet of grid. So that's why we extended that top layer. Once you get to wall heights over 10 feet in our AB wall software, we then also extend the second top layer of grid to that same amount. So one thing to note is sometimes you might have something that's going on your site where this top layer of grid can't get extended. So let's say you have maybe some sort of fence post right here, or maybe some sort of electrical line or something where this layer of grid cannot be extended. In certain circumstances, as long as your safety factors are met, you can actually, instead of extending this top layer, we can extend this next highest layer up to that desired length. Now, once you have your extended layer of grid, what you want to do is you actually want to review our top layer. So anything above where that top layer of geogrid is, we want to analyze that as a gravity wall using the same soil parameters and the same surcharge parameters as the rest of the wall. And we want to make sure that, in this case, it's only a 1-block wall, but if you're doing 2-course spacing, you've got a 2-course wall, or 3-course spacing, you've got a 3-course wall. You'll need to analyze that layer, or that wall above your top layer of grid, as a separate gravity wall using those surcharge and soil parameters. That way, we can make sure that everything above that geogrid layer is still stable enough to basically survive. Now, the next thing we're going to talk about is our above wall structures. And like I said before, that's going to include our fences, our railings, our impact barriers. It's going to include, roadways, sidewalks, driveways, anything like that. So basically, any structure that's adding some sort of surcharge or wind load onto our wall. And we're going to start off with fence posts and impact barriers. So those things with the posts that are going to go into the ground, or piles, we're going to talk about that first. So obviously, you guys know fences are super common above retaining walls. Lots of cities or states require that walls over a certain height have fences above them, just as fall protection. That is a good idea. We always advise that for walls that are susceptible to people falling off of them. But there's a few things that you need to consider. It's not always as easy as just throwing those posts in the ground right behind your wall and call it good. That's actually not the case at all. And what we say is, because that fence is going to have some sort of force applied to it at some point, whether it be from wind loading or from impact or people leaning on it even, that's going to transfer a force into the fence and eventually onto the wall. And that has the potential to overturn the wall. So what we always say is that any positioning for posts for these impact structures or fences should be positioned a minimum of 3 feet from the back of the top course to avoid any local overturning. So basically what that means is if you look at the back of your top block, your top course, we don't want to put any posts within 3 feet of that spot. When we do that, if our fence falls outside of that, there's enough soil in between where any forces that are put onto the fence get distributed kind of evenly throughout the soil, and you don't have to worry so much about it transferring to the wall. But obviously you guys know that with fences, people don't like having that extra 3 feet in between the back of their wall and their fence, for various reasons. One, it cuts out on your usable space. Two, if you have to, take care of that lawn in between the fence and the retaining wall, it can be difficult to get, say, a lawnmower there or do any landscaping there. So oftentimes you will see that fences are within 3 feet of the back of the wall. And, I just said, hey, we say keep a minimum of 3 feet in between your fence post and the back of your top block. So is it okay to have a fence within 3 feet? And the answer is yes, as long as you design properly for it. And what that means is every fence that falls within 3 feet from the top of the block, you need to consider fence overturning forces in the design. So, like I said before, if that fence is within 3 feet and it has a wind load on it or an impact load on it, some of that force is going to get distributed to our wall facing, and it's going to push it out and kind of try to get it to overturn, and that's what we want to avoid. So if you are going to have that fence within 3 feet, we need to consider fence overturning forces. Now, some other things with fences is we do have some common numbers that we use, or that we would advise, I guess, using is, and that one of those is 50 pounds per lineal feet of fence. So that's going to go along the top of your fence or railing, and basically for every lineal foot of fence, you're going to have 50 pounds as a loading because of that. Or the other thing that we say is at every post, we're going to have 200 pounds of a point load at that spot. There's a ton of things that goes into post design, so obviously that can get considered a load as well, and we want to make sure that we account for that. And sometimes you will actually have your loading will be a mixture of these two. They'll add up together, so a summation of the lineal pounds per lineal foot and the point load from the post. So sometimes it will be both. It's important to know when you are going to design for both in mind, or if you are only going to design with one in mind. Some people will take the worst case, so they'll choose one or the other, and some people will choose the worst case as the combined between the two. But one other thing is that these post footings, they should be placed during construction. So what that means is that sonotube that you're going to, that sonotube or construction tube that you're going to place your fence post into the ground, that should be placed while you're putting up your wall. That way, when the wall is going up and you're placing that sonotube at the same time, you can modify your grid to properly go around that tube and to properly go around where the fence is going to be. The alternative to that, so if you wait to put in your fence posts until after the wall is constructed, that's going to cause a lot of trouble and a lot of issues that are going to take a lot of time and a lot of money to do. And the reason for that is because if you wait until the wall is already constructed, then you have to have some way to get your post down to the proper depth. And Well, many people, if they are going to post hole dig, anything like that, they're going to use an auger. And if we could use an auger in this situation, it would be easy. But the problem is, in this retained zone, we don't want to use any augers. And that's because as that spins down and kind of drills into the ground, there's a chance that if it hits a grid, it can actually grab onto it and kind of twist up and pull it out of place. And that's going to, one, it's going to stop it from being taut and tight like we like our geogrids. And two, it's going to misplace it and put it in a spot that it wasn't meant to be in. So we want to avoid augering at all costs. If you don't need to use a cement, kind of a cement pile for your post, you can drive posts into the ground with a post driver. But other than that, if you need to put a larger fence post in that you can't drive, or you need that sonotube put into place, you have to hand dig those holes. So you can see where putting that tube in during construction of the retaining wall is so much easier than coming through and hand digging each post hole, because then you would have to dig down to a layer of grid, cut the grid, and then dig down past that, cut the next layer of grid until you get down to the depth of your post. So you can see where that would require a lot of time, a lot of money, and a lot of effort that, quite frankly, could be saved by being proactive and doing it while the wall is going up. Now, another thing to mention is that when you have fence posts behind your wall within 3 feet of the back of your wall, there's a product you can use called Sleeve It. Now, what Sleeve It is it's basically like, think of it as like a like a sonotube that you put around the bottom of your fence post with a cantilever footing on it. And basically what that does is, if your post is within 3 feet from the back of the wall and it's put into the Sleeve It configuration, that cantilever footing on Sleeve It is going to transfer the load from that fence into the soil around your wall rather than into the wall. And it's worth noting that Sleeve It is not meant for impact structures, and they say that on their own website. But yeah, it's just a great product for any time you have to place a fence right behind your wall. It's also worth noting Sleeve It is not an Allen Block product. It's actually a product by Strata, and so it's just it's something that we see that works so great that we decided to put it into best practices. So the next portion we're going to talk about is, again, to do with above wall structures, but instead of fences, we're going to be talking about our driveways, our roads, our parking lots, anything like that. And the first thing you want to do anytime you are designing a project like this is you want to find out, well, first, what the depth of that structure is going to be, what the depth of that footing is going to be. As you guys probably know, on a site, since retaining walls have to do with grade change and grade correction, they're oftentimes one of the first things installed. In situations where there's a road above a retaining wall or a parking lot above a retaining wall, the retaining wall will almost always go in first. So you can imagine that if you place your retaining wall into its correct spot, and let's say there's a grid on the top, we'll use this picture as an example. If there's a grid on this top layer here, you can see where, if the people who are installing this parking lot come in here, you can see where when they excavate to place the base of this parking lot, they're going to hit this grid on this top layer. And that's not good for the grid, and it's not good for the wall, because the wall was designed to have this grid reach, I guess, a distance this far into the wall, and it's not because of this parking lot, then the wall is not designed properly. So it's very important to know what the depth of your base for your parking lot or your roadway is going to be, and to account for that. As you can see in this picture over here, your grid can actually be pitched at a 5-to-1 slope to go below any road surfaces or anything like that. As long as you have that foot behind the wall that goes straight back, you can pitch down at a 5-to-1 slope to 4 inches below the bottom of your roadway base in order to make sure that that roadway does not interact with your grid at all, or if they were to come back and redo the road at some point in the future, when they dig it up, they're not going to dig up your grid at all, because that's going to impact your wall negatively. Now, like I said, we just want to make sure that our grid is not going to get disturbed if the surface is removed in the future or there's maintenance done on it moving forward. It's very easy for someone to come in and take out a parking lot, but it's also easy for them to hit any grid that's very close to that base layer. So we want to avoid doing that, and the best way to do it is to be aware of what's, the parameters of that structure. One more thing to note, it may sound silly, but you can understand how people might think that if they're going to do their road while they're doing the top course of their wall, they might be tempted to just throw, if grid is supposed to be on a certain layer that interacts with like a concrete driveway, they might be tempted to just throw that grid into the middle of the concrete. And that is a bad idea, because concrete can actually kind of break down the geogrid faster than normal, or it breaks it down, and basically you're going to lose any function of the grid that's in the concrete just because it's no longer structurally stable. Last thing here on these driving surfaces or sidewalks, anything, surcharges like that, is that oftentimes if you have a parking lot or a road, along it you're going to have catch basins or manhole covers or a sort of drop structure behind the parking lot that might interact with the geogrid layer. So what we want to do is really we want to make sure that catch basins and manhole covers do not get placed in the reinforced zone of your wall. So as you can see here, if we have an example like this, if this was a catch basin right here, we want to push that to a spot where it's not going to hit any of these geogrid layers. We might push it down 50 feet where the wall isn't there anymore, or modify the slope so that it moves it away along the curb to somewhere else. Basically, we don't want anything interacting with our grid. You guys are going to hear that a lot. So that takes care of our structures above the wall. But now we're going to move on to stability of our slopes above the wall. So slopes above the wall are super common. Retaining walls are used in situations to usually get rid of slopes or to lessen the steepness of a slope and increase that usable space. And oftentimes what that means is that there's still going to be a little slope above the wall. Now, these slopes, when they're designed into the wall or designed into the site, there's a few things that you need to note, because there are limitations to how steep we want slopes above our walls. The general rule of thumb is on static design, so designs without seismic, we don't want that slope to exceed our soil friction angle. So if our friction angle for our soil or our phi angle is 30 degrees, we don't want that slope any steeper than 30 degrees. And the reason for that is because what that friction angle to the slope means is that in certain situations, that soil can only stay structurally sound at that specific angle. That's how it naturally sits. And out in nature, you might see the soil be at degrees higher than your friction angle, But the reason for that is because there could be cohesion at the time, or there's maybe your soil is slightly damp, so it's sticking together because of that cohesion a little better. So basically, when we're designing it out, we want to make sure that the slope is no more than the friction angle of the soil. Now in seismic design, that's going to be very similar, but our slope steepness is going to be limited to our friction angle minus our seismic inertial angle. And that seismic inertial angle is really going to be based off of horizontal and vertical seismic coefficients. I don't expect you to know these for each of your projects, but that's something that would be determined by the soils engineer, or it'll be in the geotechnical report. So really we would want to make sure that that slope does not exceed that value. Obviously, like we see in all retaining wall designs, we can't always meet these circumstances, or sometimes that slope has to be a little steeper. And so what can we do if the desired slope is going to surpass those limits? And really the number one thing is we have to look at global stability then. For those of you guys who don't know, global stability is basically when you take slip planes from above the wall, the earth above the wall, and you take points from up above the wall, and you take points from the earth below the wall, and you're going to connect them with slip planes. And basically it's testing to kind of see if that whole section is going to slide, or what are the chances of it sliding along that slip plane. And the steeper your slopes above and below your wall, the more likely you are to have a global stability failure. And oftentimes what you'll find is if you have very steep slopes and you run a global stability analysis, so especially on those walls with slopes that are greater than the friction angle, you might see that your global stability tells you that you're going to actually need to reinforce your soil or reinforce your slope above your wall. And so that's one thing we say is make sure you're aware if you need to do that, and we'll talk about it a little more in detail in a bit. So the next section, we're talking about compaction requirements. Pretty simple here. If you guys attended our Design Professional ABU Online, where we talked about Chapter 6 of Best Practices, one of the things there is we talked about soils and compaction. And what I'm going to say here is if you're designing a slope into your design, so you have a slope above your wall, you need to make sure that that slope gets compacted just like the rest of your wall does. And what does that mean? So what are those numbers? Basically, we're going to follow our Chapter 6 recommendations. And that's, we have max compaction lifts of 8 inches, and we have compacting to 90% of standard Proctor. And so the first part of that, having maximum compaction lifts of 8 inches, the reason for this is because the tools that you're using to compact, so your plate compactors or anything like that, really actually has a limit of compacting 4 inches, around 4 inches of your soil. So we don't want any more than 8 inches then, because once you get beyond that, there's a lot of soil that's not getting compacted at all, and you're going to run into settlement issues. You're going to run into some potential bearing issues, and we really want to avoid that. So we say every 8 inches or every course of block. The 95% of standard Proctor, that's just in accordance with NCMA section 13.5.3, where they talk about compaction. But one thing to note is that certain soils may require you to compact a little bit more than you normally would. Your expansive soils or your fine-grained soils might require you to do a few passovers rather than the one normal one. And it's also worth noting that just like the rest of the wall, we'll want to compact from the face into the slope. One more thing I'm going to say here about compaction requirements for slopes is when you are designing that out, when you are designing the slope out, what we really want you to see, or what we really want you to design for, is to design swales into the bottom of your slopes or at the top of your wall. And the reason for that is because, as you guys can imagine, when you've got a slope above the wall, what does that mean for water? Where's that water going to go? And what it's going to do is, the water's just like gravity, it's going to go straight down the slope. And what's the bottom of the slope? It's the back of our wall. And if you guys are familiar with retaining walls, or you've pretty much been through any of our presentations before, we say water is a retaining wall's #1 enemy. Any of that water that gets built up behind a wall adds a ton of pressure for the wall, and lots of retaining wall failures are caused by excess water behind the wall. So what we want to do is, according to best practices, we want to limit any water that gets behind the retaining wall. And by using a swale at the top of your wall, you can avoid any water coming down the slope and basically getting stuck right behind your wall. A swale will divert it away. As long as you have that swale move away from your wall, it'll keep that water away, so we don't have to worry about that. Now, our next section, we're talking about reinforcing the slope above. We talked about it a little bit 2 sections before, where if you're running into global stability issues or your slope above is a little too steep, it may be required to add reinforcement into that slope. Now, it may look funny having reinforcement in a spot where there's no facing, but one thing I want to point out to you guys is that when we're designing retaining walls, the facing in a reinforced retaining wall, the facing, it is providing some shear key and whatnot, but it's actually not doing a ton. It's actually not doing a ton for the stability. Hopefully, ideally, in a reinforced retaining wall, this soil mass right here is doing most of the retaining. Just the amount of weight that you've got there, and that normal load that it's pushing down and keeping it in its place, is doing a lot of the retaining for any of the pressure behind the wall. So typically, one thing that we kind of like to say is, we don't like to think of it as us designing a wall. We like to think of it as us designing a reinforced slope, reinforced soil slope. And all we're doing when we add grid to that slope above is we're extending that soil mass. So then all of this soil up here becomes part of the soil mass rather than just a added weight. And situations that you might want to add reinforcement to your slope, they're the same common ones that you've seen earlier on in the presentation. So it's going to be when your slopes are more than a 3-to-1 slope, when your slopes have poor soils, or when you've got a slope above and it's in a seismic area. Anytime there's seismic parameters. Those are all situations where you should consider reinforcing that slope. Now, when you do add reinforcement into this zone, what you want to try to do is basically your grid lengths are going to follow suit with the rest of your wall. And that way you keep it doesn't get confusing for anyone installing. You just use the same amount as you've been using for the rest of the wall. Now our last section is going to be on plantings. So obviously when you design a retaining wall, people want it to look nice, and a very, very common way to do that on residential jobs, on commercial jobs, on really any job is an easy way to make a retaining wall look even better is to add some plantings, some trees above or some bushes, flowers, anything like that, a little garden. And you may be wondering, is it okay to do that? These all have roots. These all have some impact on the soil below them. Is that going to be okay to have above my wall? And the answer is that it's usually just fine. Just like anything else, if you are going to have anything above your wall, you just want to make sure it's designed properly. So that's what we want to talk about. like I said, almost always plantings above your wall are going to be fine, and sometimes they're even going to help out the reinforced zone of your wall. Those roots can sometimes tangle in and help hold that soil together even more than your grid is doing. But like I said, we want to properly design for it. So there's a few things we want to do first. The number one thing you want to do is get a hold of those planting plans from either the landscape architecture or the landscape architect or an arborist or anyone that they've consulted on the job. If they have not, then you'll want to consult a landscape architect or an arborist. These landscape architects, they've gone through all the training it takes to really know, one, not just what looks good above the wall, but they know how each certain plant affects the area around your wall or the area above the wall. So some trees obviously have very deep roots that might not be the best fit for having above a retaining wall, but others have shallow roots that don't go super deep and might not even impact your geogrid at all. And that landscape architect is going to know which trees do that, which trees don't, or which shrubs are okay to have above a wall and which ones aren't. So it's very important to get a hold of them and to talk to them, have a conversation with them about how you should design this wall with that in mind. You'll want to make sure you understand the root sizes of the wall, or the root sizes of any of the plants above the wall, and you'll want to know that depending on the plants used, which layers of geogrids will be affected, if any. And once you do get that information with them, or from them, you're going to want to add it as a note in your project specifications to make sure that everything that you just learned from them is instructed to the rest of the people on the project, or it's in writing and it's on the project details, so that when the wall does get constructed and those plants get put in place, they're done properly and in a way that is not going to harm the wall. And then another thing with this that we want to make sure we do in our design is we always need to be thinking about water. So if you've got plantings above, if you've got flowers or shrubs, chances are it's going to need water. And on lots of commercial jobs and even lots of residential jobs in this circumstance, they're going to have an irrigation system set up. And as those plants get watered, where is the rest of that water going to go? And chances are it's going to go right behind the wall and down into that infill zone of the wall. And we just want to make sure that we have very proper drainage. If we can avoid the water getting back there at all, we want to do that. But if not, we want to make sure that we have the drainage to properly get rid of that incidental water so that it does not build up behind the wall and add that hydrostatic pressure. And then, obviously, like I said before, we never want to use an auger in the reinforced grid zone. And that goes the same for planting trees and planting anything as it did for fence posts. So in review, there's a few things that I want you guys to remember from this presentation. The first thing is that we need to know when we need to extend our top layers of grid, and we need to know how much we need to extend them by. So like I said before, we want to extend to either 90% of our wall height, or we want to extend our grids by 3 feet. So it's important to know the situations like when you have a surcharge above affecting the infill zone, or you have a slope above. Those are the times to extend that grid. We also need to know that fence posts should stay outside of 3 feet from the back of the top block. That's the ideal situation. Obviously, sometimes fences have to go inside of that 3 feet. While we would prefer it to be outside of the 3 feet, they can go inside the 3 feet as long as they're designed properly, and that fence overturning, that local wall overturning because of the fence is taken into account, and the calculations are done to make sure safety factors are met. Now, we also want to know that if we do have slopes above the wall, we need to know if they're going to be reinforced. So those situations where we've got slopes that are greater than 3:1, slopes where we've got poor soils, or slopes in seismic areas. Those are all the times that we want to make sure that we are reinforcing our slope. And then when we do reinforce slopes, or I guess any slopes we have above the wall, we want to make sure that they're compacted just like the rest of our wall. So we want to compact at those 8-inch lifts, and we want to compact to 90%, 95% of Proctor in accordance with that NCMA design. So those are the important things to remember about compacting for our slopes above. And then lastly, plantings. Plantings are okay. They're almost always okay. We just need to make sure that we run it by with the landscape architect to make sure that it's not going to negatively impact our grid layers. We just need to be aware of the limits of each of these plants that we're going to put above our wall. And we also need to know all about the irrigation system that might be there so that we can be aware of any water that might build up behind the wall. So that takes us to the end of the presentation. I see that we have a question. It says, is the requirements for fence design, does that apply to guardrails? Guardrails are very similar. Yes, obviously, we like to keep our guardrails back that 3 feet from the back of our top course. And the only thing is, it's a lot harder for those guardrails to fall inside of that 3 feet. Oftentimes, if you have a guardrail inside of that 3-foot zone, it's going to have to go down very low into your wall. Those post spacing, or that post depth is going to be very deep usually for impact barriers. And then the design load on the guardrail, that just gets taken into, so you asked how about the design load on guardrails? It's dependent on the type of impact barrier that it is, and I've seen some up to 6,000 pounds. I just did a fence overturning calculation for, but basically it's all going to depend on it. But that does get used in the overturning calculation for that fence. Are there any other questions? If you do have any questions, feel free to just type them into the question section. Tree weight, again, it's going to be very dependent on which type of tree you have. And this is a perfect example of when to talk to that landscape architect or when to talk to that arborist, because they know, or I guess they'll be more familiar with what the proper loading for a tree would be, and if it even will, the loading will affect the wall. Sometimes the root systems distribute the load enough to where it's not going to impact the wall. You said they usually don't want to comment on a specific number. I will say if that's the circumstance where a landscape architect doesn't want to comment on a specific number, they would know better than we would. So if they aren't comfortable with providing a number for that, I would assume that we also wouldn't be comfortable spitting out a number. We are more focused on the retaining walls than the trees around. Are there any other questions? Can a fence be mounted on top of the wall, assuming proper hardware? Technically, yes. I've seen walls where they're bracketed onto the top of the wall. It does make the design a little more complicated. There are also situations where the fence can actually be grouted into the cores of the block, as long as it's designed properly. We do have some details on that on our website. But yeah, again, it's obviously going to contribute to overturning a little more the closer it gets to the face of the wall. And if you are mounting a fence on top of a wall, it's not going to have much in terms of stability, but it can be done. Any other questions? Okay, it's looking like we don't have any more questions. Again, I want to thank you guys all for taking the time to sit through this presentation. I know it's always busy, and taking an hour out of your day is never easy. So again, I do appreciate it. Like I said, this is the last of our best practices series for our Designer ABU Online, Design Professionals ABU Online. I will send out a follow-up email either today or tomorrow that will include my contact information. It'll include a link to this same presentation in a YouTube format, and it'll also include some nice links and an evaluation form to fill out in order to receive that continuing education. But yeah, so be on the lookout for that email. It'll have all that information on it, and I encourage you guys to, I guess, read the rest of best practices if you haven't. There's a ton of great information. This is only one of 12 sections in there. So get to know that document as best you can. But with that, I will go ahead and end the presentation. But thank you guys for attending.